Hey everybody, and welcome to the second video I'm making on your notes for Euler's method. Now what we're going to be taking a look at is, now in the last video we kind of ended the video showing you how you use information given to you in the problem by saying, okay, well, this is the expression for the differential equation. Our step value, meaning our delta x, is going to be something, and we have some initial conditions that we can find, and we have to be able to find what our new y value is. And we definitely do need to make sure that we're kind of paying attention to that. We're going to say, well, our new y values have to be found by taking delta y. We need to know what that is. So we have to take the slope of the value and multiply it by delta x, whatever that happens to be for the problem. And then you can add the previous y value on it to find the new y value of your function. So now that we have that in place, let's go ahead and take a look at a couple more examples that are going to be much more in line to what you could expect to see on a multiple choice type AP test question. So in this example, it says, show that Euler's method for the differential equation 0.5 times x plus y with the initial conditions of x being 0.2 and y being 1.11 go through two steps with a delta x of 0.05 and show that it's going to give you 1.1775 when x is 0.3. Now, because these are your notes and they're not exactly trying to give you an AP kind of multiple choice question here. They're telling you what the answer is in advance. Normally, what it would be is that this stuff here, the answer wouldn't be there, obviously. It would just say use two steps to say what the y value would be at that point. So let's go ahead and try working this out. And I strongly encourage you to go ahead and try pausing the video if you feel comfortable enough to do so, and work the problem out in advance ahead of me, and hit play and see what you wind up getting. So here, dy, this is that middle column. This is where a majority of the work that you're going to be looking at comes from. So dy is going to be found, dy is going to be found by taking whatever the expression for the exponential function is, and this, or not exponential, differential function, which in this case would be 0.5 times the sum of x plus y. Now we have to multiply that by delta x, and that's what dy would be. And then we would take that and we would add the previous y value to get the new y value. So knowing, having that information on hand, we can go through our first step here and say that here we're going to say 0.5 when x is 0.2 from our initial conditions plus the 1.11 times delta x, which in this case is 0.05. All of that will give you the new, or the change, the dy essentially, the derivative of y. And but that's not what the y coordinate is going to be. We have to actually take that and add it to what the previous y value was. Well, the previous y value, the only thing we have is a 1.11. So if you add all those things together, we're going to get a y value of 1.14275. And so that will be the y coordinate of the 75 of the next row. And so what's the x coordinate going to be? Well, that's just easy. You just add the delta x to it. So 0.2 plus 0.05 is going to be 0.25. We'll go ahead and just put the 0.3 here. And so this is where we have to stop, is when x is 0.3. So we're just going to go through the step process one more time with our new x and y coordinates, and we should be done. So we say the 0.5 from the differential equation. Now in this case, x is going to be 0.25 plus the 1.14275 number that we got there, and times delta x 0.05. So this is telling us how much y is going to be changing. This is what the derivative of y is going to be. So now we add the previous y number to it, the 1.14275, and when I do, I'm going to get a y value of 1.7757. And so my numbers, when I did them, I have that extra 7 at the end here, but this is essentially where it's telling us to stop, 1.7757. Just go through the 2 steps to get to there. But again, they gave us the answer in advance, but as a test question, it would say what would be the approximate y value after doing 2 steps, and you'd have to do the work to get to there. Now, taking a look at the next example here, again, this one could be adjusted in such a way to make it a very easy question that you could see on a multiple choice portion of your AP exam. Here, what it's telling you to do in this example, it says approximate 4 points on the solution curve where they're giving you the differential equation of negative 3x squared times y, and the initial conditions are when x is 0, y is 2, and the change in x is always going to be 0.1. Now here, this just is asking us to essentially go through the Euler's method through to complete 4 steps here. So this column on the right, this entire column is essentially going to be the answer for this particular question. Now, the way I would change it for an AP question is I would just say maybe through the 4th step, what would y be? And so you'd have to still go through the whole process, but we need to fill in the entire table. Now, again, I encourage you to go ahead and pause the video and try working the, filling in the table in advance of me and then hitting play and see if your answers and mine agree with each other. Now let's look at the middle column, or not the middle column, but that really wide column where they're saying delta y. Okay, this is what we've been doing. We're taking the change in y is still going to be the previous delta or y prime times delta x, and what we would do is we would take the whatever that expression is, and we would add it to y naught, or our previous y value, and that's how we get our, our new y value. So let's go ahead and go through the first step. We don't have to do anything for that initial row of P0 because they've already essentially given us the answer. So the step value is going to be pretty easy to fill in the x column. So we're going to say 0.1 here, 0.2 here, 0.3, and 0.4. We're just using the delta x to fill that column in pretty easily. Now we just got to figure out what y is going to be. So this is where the work comes in. The expression that we have for our differential equation, we start off with by saying negative 3 times, in this case, x squared. So we're looking at these numbers here to figure out what our new y value is going to be. So when x is 0, we square it times y, which is 2. And all of that has to get multiplied by delta x, which is 0.1 in this case. And then whatever that is, we would add the previous y number to it, which the previous y number is a 2. Now the stuff on the left of the plus sign, because we're multiplying by 0, all of this becomes 0. And so we say 0 plus 2, so our new y number is 2. So we haven't really made much change here. So when x is 0.1, y is 2. So that would be our answer for our first step. So now we continue. So now I'm going to say negative 3, and I'm going to take a look at the x and y value from the previous answer. So x in this case is 0.1, and I square it, times the 2 times delta x of 0.1, and plus the previous y number, which in this case is still a 2. So you do all of that stuff on your calculator, and you're going to get a 1.994. So my answer, if I did 2 steps, I would have x as being 0.2 and y of being 1.994. And we're going to just kind of continue in that fashion. So we have negative 3 So the previous x number is 0.2 in this case, squared, times the previous y number, which is 1.994. Delta x is still 0.1, and we're going to add the previous y number of 1.994, and that gives me my new y number of 1.970072. So the solution for my third step would be zero point 0.3 and 1.970072. So hopefully this is, you're starting to pick up on the pattern of how you're using Euler's method here. And so for the fourth step, and we have to go through four because it's asking us just what would it be for all four. That's what the question is asking. We're going to say -3 times the previous x number of 0.3. Now for the y number, I'm going to round it here, 1.97 squared times delta x of 0.1 plus the 1.97. Now in my calculator, obviously I'm not rounding anything, but when I type all of that into the calculator, I'm going to get 1.916880056. So my final solution here, if we were asked to say, well, what is the x and y values of the fourth step? You could say that x is 0.4 and y is 1.916880056. And that essentially is how Euler's method is performed. Now, moving on here to the next bit of your notes, the next thing it's going to ask you to do is says, how do you determine what the accuracy of Euler's method is going to be? Because it's clearly either going to be an overestimate or an underestimate depending on the curve of the function being concave up or down and whether our tangent line lies above it or below it. And if you recall from the first example, this is what we had. dy dx was equal to y. That was our differential equation. And if I solve the differential equation, this is what we wind up with, as y is equal to e to the x. And at the time I said, well, go ahead and compare the two values. So here we have our Euler's approximation, and here we have the exact values. And so if I wanted to compare them to see just how accurate they would be, is I would take the corresponding y value from my Euler approximation, and I would subtract it. I would take the difference with the actual solution at that point, and that is how we would be able to determine what the accuracy would be. Now, coming here is essentially just asking you, how do you know what kind of estimate it will be? Why do the approximate y values underestimate the actual values? And this is a pretty simple explanation. The tangent lines are below the function or the curve, and the curve is concave up. And that's what causes the Euler approximations to be an underestimate, because we're below our tangent lines lie below a concave up curve. So here, it's just asking you, okay, well, what would the difference be? Complete the table comparing the difference between the exact value and the approximate value. So subtract the approximate value from the exact answer, and make a determination, are the approximations getting better or worse? So let's go ahead and fill in the table here. So here, definitely use a calculator, just subtract the one number from the other number. And so here, we wind up with 0 for the first difference. The second one is going to be 0.00517. The next difference will be 0.0114. The next one would be 0.0188. And the fourth difference would be 0.0277. And then the last one, 0.0389. Okay, so the question is asking, are the approximations getting better or worse? Well, the difference between the exact answer and the approximate answer is growing as x grows. And in order for the approximation to be as close as possible to the real answer, we really need it to be close to 0. And as you can see, as the table continues to grow, the difference in the actual and the approximate numbers are growing. So because that difference is growing, the approximation is getting worse. And the easiest way to explain why in this particular example is our solution, which we had y is equal to e to the x power. It's growing. And I know I'm not being very specific here by saying it's growing, so don't follow that as a bad example. You make sure you say the approximations are getting worse because the function is growing at an exponential rate, meaning that the y values are going to get very, very big very, very quickly. And down here at the bottom, what can be changed to make the Euler solution curve, the Euler solution curve more accurate? Well, the easiest way, which is going to just make things more tedious and complicated, or more tedious and time consuming, the easiest answer is to say how you can make Euler's approximation more accurate. Make delta x smaller. The smaller your change in the x values, the more accurate your approximation will be to the actual curve. And the last thing that we're going to be looking at in our notes here is just kind of walking you through how you can graph the differential equation into a graphing calculator and see how things are going to change. So this is something that you can kind of do on your own. The one thing that I really, really want to make sure that you're clear on is when you're entering the function, if you notice, when you go to where it says graph entry and then differential equations, this is where you're going to say how you're going to get your slope field. If you notice, this says y1, so the function itself has to match. So when you type in your differential equation, make sure you type in y1 minus 2x in this case. And then from there, you'll go to, it'll show you that we are going to be doing a slope field. And then as you arrow down on there, this is what you're looking for plot step. You're going to change it to 0.25 because that's what this particular problem is asking you to do. And then you can go ahead and graph your slope field. Now the one thing it's asking you to do, this is really just illustrating how changing delta x is going to increase or decrease your accuracy, because it's asking you, okay, well when you graph it, great, see what it looks like. And then change delta x to be 0.5 instead of 0.25, and then change delta x to be 0.05, and see just how much closely your points that make up so these points, these dots here that make up the Euler approximation, you can see just how much closer or further apart that they're going to get based off of how accurate they are by making delta x either bigger or smaller. But that's going to be it for this lesson on Euler's method. If you have any questions, feel free to go ahead and get in contact with me. And until next time, guys, thanks for watching and take care.